All right, everybody, we got through our roadmap. We're ready to do some reaction type predictions. I'm pretty sure on one of yours you'll be asked for either the full Lewis structure of a leaving group or some kind of structure for a leaving group, like TSO minus, draw all pi bonds is another favorite. Want to start there? Which part of this thing is the leaving group? This one here, Lg right there. Lg, that's nitrate ion. O, N, O, O. It's a strange one because, you know, it's NO3 minus, which is 5 plus 18 plus 1 equals 23, 24. So I'll see students do this by mistake. They will. They seriously will. And they won't do that. Only my computer does that to me. So what's wrong with this? Tell me what's wrong. Everything looks good. It's got 26 electrons is what's wrong with that. Oh, you can't do that. Yeah, there is a pi because there's too many. Yeah. And because you did that, there's formal charges in 3 locations. Just remember. There you go.
What does you write only O and O2?
You didn't draw a full Lewis structure. I might give you half a point. He asked, what would I get if I wrote ONO2 minus? I'd probably give you 0.5 out of 2. Because there's no Lewis information at all. This would get 2 out of 2. Okay. So we got to do our analysis. Don't be predicting products before your analysis. RX in green, blue new, solvent in red, and RX is secondary, just secondary, right? Not allylic, but if I'm going with an SN1, if I am, then I'm going to make a secondary cation because you just said so. You said SN1. As soon as if you say SN1, then you're going with a carbocation. Agreed? If you're going with a carbocation, you can move an H from an adjacent position to get a better secondary allylic carbocation. That should be your first thought. And I'll tell you what makes a secondary carbocation possible, and there's only one thing, and it's red. Yes, you cannot generate a secondary carbocation unless your solvent is polar protic. Winner, winner, chicken dinner. We have a polar protic solvent in this question. But that's step 3. Let's do step 1 first. RX is currently secondary. You're saying SN1 or 2, I don't know. That is about as short as you can get that. Tell me what you're analyzing. Tell me what category it's in. Tell me what conclusion you're giving. I need a minimum of 3 things. I'm analyzing the nucleophile. Categories are strong, medium, poor. Which one do we have with an alcohol? Weak or poor. I'll take either word. Both are okay. Anything that reflects a negativity, you know, in terms of reactivity. So poor favors not the one where there's backside attacking going on. What's the other one? Oh yeah, I'm starting to think of cations now. I'm starting to think rearrangements. Solvent looks like it's missing. ROH was both the nucleophile and the solvent. Don't tell me it's a poor solvent. There's no such thing. All solvents are good. All right. So what category solvent? You need polar protic, polar aprotic, or non-polar? Polar protic, PP. Don't write PP. Write polar protic. Also saying SN1. I got blue saying SN1. I got red saying SN1. I'm thinking SN1. I'm thinking carbocations. I'm thinking I better draw my carbocation.
I have a question.
Yes, ma'am.
So when I see heat, I immediately think either E1 or E2. And then I see that it's not, the NU is not strong, so I rule out E2.
Yeah, there's no elimination E2 for PKB equals 19. Why is PKB 19 for HOCH3? It's the conjugate base of an oxonium. 14 minus -2 or -3. -19, -20, right? 17, wait, 14 minus -3 is, 19 is not a possibility, is it? 14 minus -3 is 17. 17 or 18 were my two possibilities. Yeah. Heat is only a thing if you have a strong base. Otherwise, this was just a slow SN1 reaction. Again, I think that's not the first time it's come up today, right? Please find the other video where I said, well, hey, this is not really for E2, in which case it wasn't even a possibility because there was no strong base then either. I didn't have to say it, but I wanted it to be clear. So there is your original cation. I drew it. What can this cation do to become a much better cation? Hydrogen shift. Secondary is going to become secondary allylic, which is going to give all of our major products. Looks like there's only one. Copy that. New bond to what? Right there. Major SN1 product. New bond to what atom? O. With a CH3 attached. Now tell me why this, or what kind of product this one is. Sorry about my colors changing. That's from the original cation, isn't it? Not as good. Therefore, less amount. I don't want you to think the CH3 is attached to the green there. There. There's your two SN1 products. One with a rearrangement to a better cation, secondary allylic. Same stability as roughly 3.5 degrees. Stability, that's why it's SN1 big time. Minors, you got lots of choices. I just need alpha, beta to either cation. Okay? I don't really care the order of these last three. I can go from the bottom cation and get this. I can go from the bottom cation to get this. 1, 2, 3, 4, 5. That's E versus, no, that's not E versus Z. How about E versus Z here? There you go. No, this one is E, and this one is Z. So those are different geometry. And the terminal doesn't have geometry. If I had to put these in order, I would say major of the three last minors, this one highest amount, second highest amount, and a terminal has only one carbon attached. It's the worst. So for future reference, most minor, second most minor, and middle minor. Most minor? No, I can't say that either because this one's a higher amount because it's an SN versus an E, right? These two both in higher amounts than any of those. Yes. Yeah. This one moves and becomes cation there? Less stable. Yes, you can use it to predict more products. I'd give you points. She was asking if she wanted to resonate this to get this, would I accept her new products? And my answer is an emphatic yes. You could add boxes that result from that cation right there. Okay? So you could add an SN box from that, where the OCH3 ends up there. You could put another double bond. Well, really, you shouldn't put a double bond there. Because, you know, I'd take it. I don't like it. It's hard to get adjacent double bonds. That's all I'm saying. And I guess that's all.